Hi, I'm Hannah Bonvecchio, and this is my Lab 4 on oscillations. The purpose of this lab is to examine the motion of an oscillating spring mass system, compare the predicted amplitude and period of oscillation with the observed amplitude and period of oscillation, compare the predicted position and observed position, prove whether the energy principle holds true, and then our results. The predicted position of the model will underestimate the observed position because a person dropping an object will probably add an initial force unintentionally, increasing the velocity for the observed position. Assuming the system loses no energy to heat or external forces, the sum of the energies of the objects in the system should equal 0 since energy is conserved. The important physics fundamentals to know for this lab are the formulas for change in kinetic, potential, and spring potential energy, as well as for period and amplitude. Basically, finding change in kinetic and potential energy are pretty much the same, where K equals 1/2 mv squared, UG equals mgd, and US equals 1/2 KS squared. And then you find the change in energy also the same way, and then your total energy is just the sum of all of those. And your period is using your angular velocity divided by 2 pi, or you do the time divided by the number of oscillations, and then you can find amplitude using this formula, or you can just measure it. So for this lab, you can either perform your own experiment or use a video. I decided to use the video, so I used initial conditions from the pre-lecture video number 51, and those are a mass of 0.402 kilograms, calibration length of 0.7 meters, 10.5 seconds between frames, and then their frame rate was 0.095, and then other physical characteristics of the system were the spring constant, 6.83, and then the relaxed length of the spring, 0.123 meters, and then the initial position being 0, 1.1 e to the negative 16th 0, and then the total time was 9.69 seconds. Next, we identify our system and surroundings. So our system is the spring, the mass of 0.402 kilograms, and the earth. The surroundings are basically anything that is not included in the calculations. So that includes the board behind the spring, the floor, literally anything. Then, after this, we are going to open Tracker and use point mass to track the mass as it oscillates. And this is what that looks like in Tracker. Next, we're going to make our computational model. We're going to edit these lines in our starter code. So we're going to input our initial conditions, so our mass, our position, and our velocity, and then start time at 0, step it by whatever you want. And then we're just going to set our variables here. Then we're going to find our formulas for our energy components. So basically that's what all happens here, and those were also listed on the formulas to know. And then we calculate our net force here of using the spring and gravity. Then we're going to update velocity position of the spring, and then after that we will calculate energy changes. Next, you're going to import your data into your computational model, and that's just basically throwing all of this data into an Excel spreadsheet, only X and Y, no time, and don't include any labels, and then export it as a .csv, and make sure that the data starts on row 1 or it won't work. Next, you will basically select what file you want to use, and that was that Excel file, and then when you run it, it looks like this. And that basically means it ran correctly. And then we see in the change in energy graph on the right, basically that the sum of all of the energies equals 0, which basically means that our energy principle holds true. When we compare our predicted or our model position to our observed or experimental position, we see that the model underestimates the amplitude and overestimates the period of oscillation of the spring. The experiment moves further from the origin than the model by 0.1 meters in the x and 0.04 in the y, and this experiment oscillates at a faster period than the predicted model. Possible sources of error come from tracker error, so with the calibration stick, estimating where the CM is for point mass or camera angle. There could also be error due to the inaccuracy due to a collision of the mass with the board behind the mass. I think it moved the board, which could have accelerated the mass. And then the initial velocity was larger than the observed position than in the model, so the person dropping the object probably added a force, adding some velocity. For the model system, is the energy principle satisfied? Like we said earlier, the energy principle is satisfied because the sum of all of the energies in the system equals 0. Therefore, energy is conserved, and that's what that graph shows. And then using data from Tracker, we made 2 separate estimates of oscillation periods in the X position data and then the Y position data. and then we compare the two. One is 1.65 average, one is 1.52 average, and since the periods of oscillations were within 0.13 of one another, the graph of the oscillation is relatively accurate. Taking an estimate of the periods in x and y, the true period of oscillation is around 1.6 seconds.